Hi everyone, my name is Rose Vagatus, and I'm here to talk to you about my Stats 512 individual project covering the influence of several soil characteristics on the soil pH. Whether we know it or not, plants serve a critical role in every form of life survival. And at the root of all life are the nutrients required by the plants to ensure optimal growth and development. The Liebig's Law of the Minimum explains an important concept of how plants' potential is restricted by the most limiting resources. This law is easily explained with the illustrations shown on the slides. Imagine that a corn's plant optimal yield potential is represented by the brim of the barrel. In order to reach those optimal yields, all nutrients need to be present at adequate levels. Yields are reduced if one or more of those resources are deficient. Many of the nutrients displayed in Figure 1 can be classified into two categories, micro and macronutrients. What distinguishes the macro and micronutrients from each other is simply the quantity required by the plants in order for survival. It does not imply the importance of these nutrients. A few examples of these nutrients' role in plant health and development are noted on the slides. Over the years, numerous studies have proven that plant availability of these nutrients is significantly impacted by the soil pH levels. This knowledge has been beneficial for the development of graphics similar to those shown in Figure 2. With this knowledge, we want to know whether pH levels can be predicted based on known concentrations of various micro and macronutrients found in the soil. This theory can be tested by setting all beta values equal to 0. Therefore, we'll know that at least one of the betas have a significant impact on the linear regression if the p-value is less than 0.05. Additionally, we want to determine if all variables in the full model provide an added benefit of information to help predict soil pH. In other words, can any of these variables in the full model be dropped? Lastly, I would like to determine the impact of each predictor on soil pH. To test this hypothesis, I used soil data collected from the Teslas project in Ireland, which covers approximately 13,000 square kilometers across 6 counties. This data contained 3,475 composite soil samples that were collected within a 20 by 20 meter square every 4 square kilometers to a depth of 15 centimeters. These samples were used to analyze approximately 50 different trace elements, soil pH, and loss of ignitions. For the purpose of this project, the sample size was reduced to the first 1,000 samples, and the explanatory variables were reduced to the 8 displayed on the slide. It is important to note that the loss of ignitions is an indirect method used to measure carbon and organic matters found in the soil. The first actions were to evaluate several characteristics and assumptions of the full model, which is written at the top of the slide. The residuals versus fitted plot on the right suggests that the predictors have a linear impact on the soil pH. This is confirmed with the summary output that contains an F-statistic of 169.3, which is greater than the critical value of 1.889. Therefore, we can reject the null hypothesis and conclude that one or more of the betas does not equal 0. Next, a quantile plot was generated to check the normality of the data's residuals. This plot suggests that the data violates the assumption and was further investigated by running a Shapiro-Wilks test. With a p-value of 2.2 times 10 to the negative 16th, we can reject the null hypothesis and conclude that the data does in fact violate normality. Additionally, the Brown-Forsyth test was ran to check the equivariance of the residuals. From these results, we can again reject the null hypothesis and conclude that the data does not have equivariance among its residuals. Lastly, histograms for each variable were generated to look for potential outliers in the dataset. From these graphs, it appears that each variable has one or more potential outlier with the exception of loss of ignitions. Further diagnostics and remedial methods will be discussed later in this presentation. From the graphs, we can also see that all variables with the exception of loss of ignitions are extremely skewed to the left of the plots. Based on the preliminary analysis, several transformations are needed to amend these violations. As shown in the previous slides, none of the variables in the model followed a normal distribution. An attempt to improve the distributions was completed by performing a log, square root, and exponential transformation on all x variables. Results found that the log transformation did the best job at fixing all x variables and are shown on this slide. Following the transformation, assumptions were rechecked with the Shapiro's-Wilks and Brown-Forsyth test. These results shown that the transformation on x variables improved the normality and equivariance of the residuals. However, they were still in violation of these assumptions. The next attempt to fix the issues associated with normality and equivariance was by conducting a Box-Cox transformation on the transformed model. The Box-Cox function computed a lambda value equal to negative 0.94. This value is close to negative 1, therefore 1 over y was used to transform the soil pH values. The assumptions were rechecked following the transformation. Here you can see the improvements made on the normality and equivariance assumption violations following each transformation. Following the Box-Cox transformation, the equivariance issue was finally resolved as shown with the final Brown-Forsyth test. Although the normality assumption is still in violation following the Box-Cox transformation, we can see that the normality was substantially improved compared to the original model. I would like to briefly note that the Box-Cox transformation was attempted without an X transformation to see if the X transformation was truly necessary. However, the Box-Cox transformation alone did not do a satisfactory job of fixing the normality and equivariance errors. Now that the appropriate transformations are applied to the model, additional methods and functions need to be applied to the transformed model to determine if any variables can be dropped. The first steps in the model selection process was to run the best subset algorithm. The lowest malloc CP, AIC, BIC, and PRESS P values, along with the highest adjusted R-square values, are highlighted in red. These results indicate that either Model 5 or Model 6 may be the most appropriate subset model. To aid in the decision-making process, the stepwise regression and the k-fold cross-validation methods were ran. The information on these slides provide the results generated by the stepwise regression model and the k-fold cross-validation. The k-fold cross-validation reveals that both Model 6 and Model 5 have similar RMSE values. However, Model 6 has a higher R-squared value. Both methods determine that the Model 6 is the best subset model. From the added variable plots, it is apparent that all variables are contributing some degree of additional information to the regression. The variables providing the most information to the regression appear to be the loss of ignitions and sulfur, whereas the least important being magnesium. Next, the assumptions were reevaluated to determine if further remedial methods were necessary. One of the first steps completed to assess the reduced model was to check for influential outliers. This was completed by running a Cook's distance, influence plot, DFF fits, and DF betas in R. The results displayed on this slide are the outputs from the Cook's distance and the influence plot functions. The influence measure function generated the results shown in the table. As seen here, none of the cases for the Cook's distance exceeded the 20th percentile of 0.546 or the 50th percentile of 0.907. However, cases 495, 497, 505, and 821 appear to be outlying X variables with a high influence because their hat values are greater than 0.014. Additionally, 14 points were shown to have a significant influence on the regression since the DF fit values are greater than 0.167. The which function in R was used to locate the 14 cases in the dataset to sort through 1,000 samples. No observations appear to be influential based on the DF beta values since all values are less than 0.63. Despite the discovery of these influential cases, all cases will remain in the dataset since there are no evidence that these values were caused by human or equipment error. Additionally, the nutrient concentration values listed in the original Excel file are realistic with soils in Ireland. A remedial method known as the robust regression was applied to the best fit model to reduce the impact that the influential cases have on the regression. This was done using the Huber estimator weight function. This function scales the residuals and uses the median opposed to the means. This is done since the median is more resistant to the impacts of those influential outliers. therefore improving the accuracy of those parameter estimates. This is shown in the summary results since the residual standard error was reduced after implementing these methods. Additionally, the normality and the equivariance of the model was improved after implementing the robust regression. Lastly, several functions were ran to check the multi-collinearity of the variables used in the best fit model. From these results, we have no signs of collinearity, especially since none of the VIF values exceed the threshold of 10. I would now like to wrap up by briefly discussing the results and the discoveries made while generating the final model. As mentioned very early in this presentation, the null hypothesis stating that all betas in the full model are equal to 0 can't be rejected since the p-value is significantly less than the alpha value of 0.05. To address the remaining research questions, several methods were applied to determine the best fit model. Through this process, it was discovered that dropping potassium and zinc would provide the best model and was confirmed with the k-fold cross-validation. To answer the final research question, a summary output following the application of the robust regression was used to build the regression displayed in the gray heading. Here we can see that the magnesium, manganese, phosphorus, and sulfur have a negative impact on the regression. Additionally, molybdenum and loss of ignitions has a positive impact on soil pH. This regression can be useful to predict soil pH levels when all nutrient values are known. However, recall from earlier in the presentation that two transformations were applied to the data. In order to make sense and interpret the regression outputs, these transformations need to be reversed. First, the Box-Cox transformation needs to be reversed by raising the transform y value to the -1. Secondly, the log transformation on x must be reversed by raising the transform x value onto 10. When using this model, keep in mind that it was developed with non-normality still present. Also, the model developed in this project is practical for a regression course, such as Stats 512, however, is not practical for a soil science perspective. The complete list of elements used to develop this best fit model are not the only ones present in the soil, and can be found in numerous complex forms and oxidative states. Other soil properties such as cation exchange capacity, parent material, and the presence of 2-to-1 clays can also play a role on soil pH. Recommendations for future analysis would be to perform a pairwise comparison between the variables as a way to compare the micro and macronutrients impact on soil pH separately. Several studies have been published from the soil data collected from the TESLAS project. The paper used for this class project was the Mapping Trace Element Deficiencies by Co-Krieger from the Regional Geochemical Soil Data, a case study on cobalt for grazing sheep in Ireland. The objective of this study was to spatially document the concentrations of trace elements across Ireland. The authors used geostats to analyze the data, specifically co-Krieger, which is essentially the multilinear regression equivalent in geostatistics. When analyzing the data, the authors applied two transformations to the data. One was a log transformation on the x variables, and a second was a Box-Cox transformation. Further remedial methods included the normal scores transformation. For my project, the soil data collected from the TESLAS project was used to develop a regression model to predict the soil pH levels based on known concentrations of various nutrients found in the soil. Similar transformation methods were used on the data as the original paper. However, the Huber estimator robust regression method was used to reduce the impact of influential cases. Attached on this slide are the citations for the publications referenced for the project and the links for each figure shown in the presentation. And lastly, I would like to thank everyone for taking the time out of their day to suffer listening to my Stats 512 individual project.